Good morning, everyone. We'll get started with session number 3.
Okay, good morning, everybody, and welcome back. My name is Paul Torrens. I'm a professor of computer science at NYU, which is 2 rivers away, the Hudson, and then we're on the Brooklyn campus over by the East River. So we have a wonderful session to kick things off today on animation and voxels. We've got 4 really great papers. The first one is going to be online. It's hierarchical neural skinning, deformation with self-supervised training for character animation by Chanyi Wang and Xihuang Liu.
Ladies and gentlemen, I am Chanyi Wang, a master's student from Tianjin University, China. Today, I am excited to present our work titled Hierarchical Neural Skinning Deformation with Self-Supervised Training for Character Animation. This presentation will be organized into the following sections: background and motivation, objectives and contributions, methodology, experiment and results, conclusion and future work. Background and motivation. Traditional geometry-based methods, widely used for real-time mesh deformations, fail to capture biomechanical details such as muscle deformations and fat wobbling. For example, linear blend skinning, LBS, Magnanet et al. 1988, which interpolates mesh vertices based on skeletal transformations, is efficient but cannot simulate complex behaviors like muscle bulging and contraction. The delta mush algorithm, Manswich et al. 2014, which improves joint deformation using Laplacian smoothing, still cannot capture dynamic muscle changes. Yilmaz's 2009 muscle modeling method based on ellipsoidal implicit surfaces is intuitive but cannot simulate dynamic muscle deformations. Finite element methods, FEM, can accurately simulate the physical behavior of bones, muscles, and fat by discretizing objects into finite element meshes and solving physical equations to achieve realistic deformations. However, FEM is computationally intensive and not suitable for real-time applications. Position-based dynamics, PBD, supports faster multilayer soft body simulations using constraint solvers to achieve physical simulations. Although significantly faster than FEM, its simplified constraints limit the simulation of complex muscle behaviors and cannot fully capture muscle dynamic responses. In recent years, data-driven methods based on deep learning have made progress by learning the mapping between skeletal transformations and vertex deformations. Xing et al. 2021 proposed Deep Emulator, which trains a neural network on spherical datasets to simulate soft body animations but relies on spherical simulation data and has limited generalization ability. Li et al. 2021 introduced NeuralBS, which learns the mapping between skeletal transformations and vertex deformations to generate pose-dependent deformations but requires large-scale labeled datasets to ensure accuracy and robustness. Sant-Esteban et al. 2020 extended soft SMPL based on SMPL to learn nonlinear soft tissue dynamics but also relies on large-scale labeled datasets. Han et al. 2024 proposed the Active Neural Network, ANN, which learns the relationship between muscle activation signals and skin deformations to reduce the dependence on labeled data but still requires some labeled data. Self-supervised learning derives the loss function from physical principles, eliminating the need for large-scale labeled datasets and reducing the cost of data preparation. Pfaff et al. 2020 proposed mesh graph nets, MGN, which learn the propagation of dynamics in physical systems such as fluids, cloth, and soft bodies through recurrent message passing blocks. Dalton et al. 2023 introduced physics-informed graph neural networks, PIGNN, for soft tissue mechanics simulation, incorporating prior knowledge of physical models to construct a self-supervised framework and reduce dependence on labeled data. Objectives and contributions. Objectives. This research proposes a hierarchical neural skinning deformation method based on self-supervised learning, combining the approximation capabilities of neural networks and the precision of physical models to efficiently generate high-fidelity character skin deformation animations with high visual fidelity, computational efficiency, and generalization ability. Main contributions. A hierarchical skinning deformation method is proposed, which uses two neural emulators to simulate the dynamic responses of musculoskeletal and soft tissues separately, enhancing muscle bulging and contraction effects as well as secondary motions, and achieving efficient and high-fidelity deformation. A self-supervised training framework based on physical principles is proposed, which eliminates the need for labeled data and leverages physical prior knowledge to improve the model's generalization ability while maintaining high computational efficiency and generalizing to arbitrary mesh topologies. Methodology. Firstly, the hierarchical neural skinning deformation framework consists of three main steps. Step 1. Skeletal muscle template. A parameterized skeletal muscle template is constructed to generate linear blend skinning, LBS, animation sequences for both skeletal and muscle meshes, as well as muscle path sequences, adaptable to any bipedal 3D character. The template includes bone segments, muscle path lines, and surface meshes. A biological parameter precomputation module calculates muscle bundle activation values, fiber direction vectors, and tendon muscle attribute values, integrating them into a parameter vector that is fed into the musculoskeletal emulator. Step 2. Inner layer deformation. The musculoskeletal neural emulator, based on a biomaterial model, captures the bulging, contraction, and dynamic responses of skeletal muscles, achieving self-supervised learning through a loss function derived from physical principles. It takes skeletal motion sequences and biomechanical material parameters as inputs and outputs the dynamic deformation results of the skeletal muscles. Step 3. Outer layer deformation. The soft tissue neural emulator simulates the secondary motion of soft tissues driven by the movement of the inner skeletal muscles, employing self-supervised learning trained with a physical energy loss function. It takes the inner layer animation and biomechanical material parameters as inputs and outputs the dynamic deformation results of the soft tissues. Next is the model architecture section. Multiscale nested graph structure. The model meshes involved in this study are modeled as graph structures and organized into a multi-scale nested structure. Central vertices are selected at each scale, and vertices with even adjacency are extracted to form coarser levels, connected by bistride edges. This iterative process creates a multi-layer nested graph with shared nodes across scales. Overall architecture. Both the musculoskeletal and soft tissue neural deformers adopt a physics-inspired graph neural network architecture, PIGNN, following the encoder-processor-decoder paradigm to process features and output physically meaningful predictions. Encoder and decoder. The encoder converts parameter vectors from nodes and edges into embedding features, consisting of node encoders and edge encoders, both implemented as multi-layer perceptrons, MLPs. The node encoder divides parameter vectors into physical and geometric components, each processed by a 64-dimensional MLP and then concatenated into a 128-dimensional node embedding. The edge encoder processes edge parameter vectors through a 128-dimensional MLP. The decoder, composed of an MLP with 128-dimensional input and 3-dimensional output, decodes the node embeddings into velocity increments for the nodes, serving as the physical predictions. MSEAMG modules and processor. The processor is composed of multi-scale edge aggregation mesh graph network, MSEAMG, modules. Edge-embedded features across multiple coarsening scales are initially processed by node updaters to refresh the central node's feature representation. Subsequently, edge updaters recompute edge features by aggregating updated nodal states from adjacent vertices, completing a message passing step. The multi-scale edge aggregation modules enable hierarchical message passing across coarsening scales, effectively expanding the single-step receptive field. Multiple message passing steps are achieved by stacking multiple MSEAMG modules, with the specific stacking configuration optimized based on task requirements and computational cost. Adjacent steps selectively process edge features at different coarsening levels, and used edge features bypass current step computation and propagate directly to next step. All modules share weights, differing only in using edge features in that step or not. In fact, we can consider that the converged MSEAMG modules are able to learn how physical laws propagate among the mesh vertices and act as a motion solver for vertices during the prediction step. To enable the self-supervised training of the neural emulators, we designed self-supervised training frameworks for the two emulators, respectively. The solution of the dynamic system can be modeled as a minimization objective optimization function from the perspective of incremental potential energy. For a dynamic system composed of muscle finite elements, the objective function for solving its quasi-static equilibrium state can be expressed as equation 1. Starting from reformulating the solution of the secondary dynamic motion equations as an optimization problem with respect to the predicted positions, the self-supervised training framework for the soft tissue deformer is constructed as equation 2. The core of solving the above two optimization problems is to describe the total energy of the corresponding dynamic system in the form of a loss function. Centered around the objective function, we construct the corresponding physical energy loss function based on biomechanical materials. The inertial energy term L inertia and the gravitational potential energy loss term L gravity are calculated in the same manner as in previous works. The muscle strain potential energy loss term L muscle strain is the key factor in supervising the predictions of the musculoskeletal neural emulator to ensure compliance with the deformation patterns of biomechanical materials. The muscle strain potential energy loss term is defined as equation 4. The strain potential energy density function psi muscle represents the internal potential energy generated by the deformation of the muscle mesh from its reference configuration to its current configuration. Psi muscle is defined as equation 5. Alpha represents the activation state parameter of the muscle fibers, where alpha equals 0 indicates fully deactivated muscle and alpha equals 1 indicates maximum muscle activation. Gamma superscript m denotes the material type parameter, where gamma superscript m equals 1 represents an element entirely composed of muscle material and gamma superscript m equals 0 represents an element entirely composed of tendon material. Both alpha and gamma superscript m are provided by the biological parameter precomputation module. Psi passive is the passive strain potential energy function, which describes the strain potential energy generated by deformation when the muscle is in a deactivated state. Psi_active represents the active strain potential energy function. We adopt the J-shaped force stretch material behavior introduced by Markert et al., defining it using a polynomial expression. For details on the construction method, please refer to section 3.2 of this work. For the self-supervised training of the soft tissue emulator, we construct the physics-inspired loss functions based on secondary dynamic motion equations. This part is consistent with our previous work. For details, please refer to the previous work in section 3.3 of this work. Experimental results. Dataset construction. This study constructed 3 human structural models, torso, upper limbs, and lower limbs, based on a parameterized skeletal muscle model, with skeletal and muscle meshes derived from the visible human male dataset. 5 different models were generated by randomly sampling skeletal segment lengths. Animation data were extracted from the KIT dataset in a mass, resulting in a total of 80,000 frames. Using a vertex blend skinning script developed with the Blender Python API, skeletal-driven surface mesh animations were converted into volumetric mesh animations. Evaluation metrics. Roll RMSE was used as the primary evaluation metric to quantify the visual fidelity difference between the generated animations and the ground truth simulations, measuring the continuity and realism of the animations and providing an objective basis for model performance comparison. Experimental environment. The experiments were conducted on a desktop workstation equipped with an Intel i7-10700 CPU and an NVIDIA RTX 3060 GPU. The model framework and training were implemented using the deep learning library PyTorch. Performance comparison of the musculoskeletal emulator. The proposed musculoskeletal neural emulator was compared against NeuralBS, CFD-GCN, GNS, and LBS. On the validation motion sequences, the proposed emulator significantly outperformed NeuralBS and LBS in terms of the roll RMSE metric, with results closer to those of the Ziva muscle simulation toolkit, demonstrating its superiority in muscle deformation simulation. Performance comparison of the hierarchical method. The proposed hierarchical method was further compared with methods using only the soft tissue emulator, NeuralBS, and LBS. The results showed that the hierarchical method outperformed other methods in visual fidelity, generating more realistic character animations, including muscle contraction and expansion as well as secondary dynamics of soft tissues. Computational efficiency analysis. The musculoskeletal emulator demonstrated significantly lower frame times compared to the Ziva toolkit, and the soft tissue emulator also exhibited good real-time performance. This indicates that the proposed hierarchical method not only offers superior visual effects but also higher computational efficiency, making it suitable for real-time character animation generation. The importance of the biomechanical supervision module in the training of the musculoskeletal emulator was validated through ablation experiments. Compared with an emulator trained using an isotropic strain potential energy loss term, the biomechanical supervision module enabled the model to more accurately respond to muscle activation signals, generating more realistic muscle deformation effects. Conclusion and future work. Conclusion. This paper presents a hierarchical skinning deformation method based on self-supervised graph neural networks. Through a physics-inspired self-supervised training framework, the method eliminates the dependence on high-quality ground truth data, significantly improves training efficiency, and maintains high visual fidelity and physical consistency. The proposed neural musculoskeletal and soft tissue emulators effectively capture the dynamic characteristics of character muscles and soft tissues. Future work. 1. End-to-end training framework. Explore an end-to-end training framework integrated with muscle anatomy embeddings to reduce the dependence on manually designed skeletal muscle templates and enhance cross-species adaptability, including non-bipedal character models. 2. Integration of high-precision supervision data. Incorporate high-precision supervision data to improve the accuracy and stability of the model in complex muscle simulation scenarios and enhance its responsiveness to extreme kinematic configurations. 3. Physics-compliant collision handling. Integrate incremental potential energy-based collision handling models into the self-supervised energy supervision framework to enhance physical plausibility in multi-body animation scenarios. Next, we will present some visual results. Thank you for your attention.
Fantastic. Thank you so much. Any questions for Chanyi?
It's, if you could come up so he can have you.
Can you hear me?
Oh, yeah.
You mentioned one of the future points that you're going to try to implement is realistic collision in multi-body systems. How are you currently handling collision in an environment with multiple things and factoring gravity into the simulations presented? Sorry, how is collision currently being handled? between the muscle skin, between the meshes and foreign objects in the simulation, such as the ground.
It's a two-step. We first use the muscle emulator to generating vertex process vertex sequence. Then we use this sequence. It means the vertex position sequence to the second step. To the surface tissue emulator. Maybe my language is a little poor.
I was able to understand that. Thank you.
Else, we can contact by email if you're interested in this. It's maybe helpful.
I see.
Okay.
Thank you.
Thank you so much. Wonderful. Any other questions for Chanyi? Please, come on up.
Can you hear me?
Yeah.
Okay, awesome. I just want to say great work. I really love what you did. It's really cool. My question is, you have the alpha parameter, which is like the muscle activation, where 0 is like not activated, 1 is fully activated. Is that a free variable, or is it like dependent on the angle of the bone?
In our experiment mentioned, the test angles all good, all perform good. Maybe we can experiment in our far more angles. It needs more experimentations, but in our works, we can 我操，怎么说呀？
You're good. You're good.
Oh yeah. Maybe we can contrast in words. Okay. Okay.
Awesome. Yeah, for sure.
For sure. In our experiment mentions, it can persist. It can persist the or wide angles.
Okay.
Yeah.
Okay. Awesome. Cool. Awesome. I appreciate that. Thank you.
Okay. Thank you.
That's great. Thank you very much. And we have probably just have time for one more quick question. No? Okay. Well, in that case, please join me in thanking Chanyi for a wonderful presentation. Thank you so much, Chanyi. Okay, and our next presenter is Florin Vladimir Stancu, Tomer Weiss, and Rafael Kufner dos Años, going to be speaking to us about foveated animations for efficient crowd simulation.
Right. So, good morning, everyone. Nice to be here. Let me start with some very quick introductions first. Hi, I'm Florin Vladimir Stancu, please just call me Vladimir. I'm a master student at the University of Leeds and the main author for this work. The other two authors are Raphael Kaufner, also from the University of Leeds, and our very own Tomer Weiss from the New Jersey Institute of Technology. I would like to begin by saying this started up as my own final year of bachelor's project, and I'm very happy to be here now presenting it to you. We'll be going to the motivation and background research, followed by the hypotheses, then the method and how we evaluate it, and then the results and discussion. So let us begin. Generally speaking, computing high-quality graphics takes tremendous amounts of computational power, be it rendering textures, casting shadows, simulating cloth movements, or simply computing the complex shading models. The costs add up exponentially. One way to combat these costs is the idea of foveated rendering, where everything within the user's fovea gets rendered at high quality, but everything in the periphery is instead rendered at lower resolutions. Existing work on this includes variable rate shading, which is what allows us to do lower resolution rendering in specific parts of the screen to begin with, followed by work by Stenger et al., which tries to make the fall off from the fovea to the periphery much more accurate to the human visual system. Then Thurston et al. Improving upon this a step further by adding luminance conditions into the equation. Now, vision science backs the idea of foveated rendering because, as you may already be aware, our human visual system's raw density gets lower and lower the further away we get from the fovea. One thing that should be clear, though, is that we don't actually see blur in our periphery, we see pooled. That's to say, the rods that we do have in the periphery all get tied up to single neurons, so the information gets aggregated. One way to say this is that actually we see statistically. We know what's in our periphery, but the details are being lost to us. This leads to a major factor called the crowding effect. If you look at the center here on the cross and you try to figure out which direction the duck on the left is looking at, you will be able to tell. If you try to do the same with the duck on the right in the middle, you will find yourself unable to do so. This is the crowding effect, where we can see and know what is in the periphery, but again, the details are being lost to us. There has also been recent work which tries to take advantage of this crowding effect and the pooling factor in general. This includes this metamer foveation, which attempts to do the fall-off, the blur in the background in such a way that the pooled information by our eyes is the same as it would have been from the ground truth. To our eyes, it's all the same. Back to our original problem, our application is more than just rendering, especially in the context of game engines. Particularly, animation updates can be very, very costly. An extreme case of this is crowds, where you have thousands upon thousands of low poly characters, all with bone transformations and mesh transformations, mesh deformations, and that adds up to be the majority cost of the rendering pipeline. There has been existing work to try and accelerate crowds. The first is the idea of 2D imposters to replace 3D agents. Level of detail based on the prominence of the agent on the screen, as well as GPU-accelerated animation updates done via instance management in the GPU. However, what you might have noticed about these things I just talked about is that none of it tries to make use of the vision research we just mentioned. So, what could we use? The first is the crowding effect we were just mentioning. The second is flicker. Work by Grachencic et al. Tells us two important things. The first is that our perception of flicker peaks in the near periphery. The second is that based on a number of conditions, including the flicker's position in our eyes, we sometimes achieve something called critical flicker fusion, CFF. What this does is that the flicker in our eyes no longer registers as being flicker, but as being static. Think of a blinking light, instead of being blinking, it's just on all the time. That's how it looks to us. The third thing we can use is the double drift effect. If you look on the dot to the left here, you might perceive the orb on the right as going diagonally left and right. However, if you look at the orb now, straight ahead, you will realize it's actually going up and down straight up. The reason why it looks like it's going diagonal is because of the internal shifting motion, which also goes left and right. The fact that our eyes mistake these two different motions as being one is what we call the double drift effect. So what do we observe? We observe that, one, in our periphery, we don't see movement accurately due to the double drift effect. We don't see flicker well, or we outright ignore it due to the critical flicker fusion. and we don't perceive crowded objects well due to the crowding effect. This leads us to our hypotheses. The first initial hypothesis that we have is that we can simplify movement in the periphery to save on computation. What you see on screen here is one such example, where the left is what it looks like fully animated, and going to the right, we see how it looks more and more foveated. We simply reduce the animation rate. However, as we were just saying, our perception of flicker peaks in the near periphery. So if you try to foveate animations, that will make them look clunky and create flicker, which might be perceived by the eyes. So we have an alternative hypothesis. We believe we can omit movements altogether in the periphery and save on computation. As we're dealing with crowds of very small agents with naturally high crowding, we believe the lack of animations will go unnoticed. We also have two further hypotheses we're going to test. The first is that the more crowding there is in a scene, the less noticeable foveation is going to be. The second is that if you have organized movement from our crowd, the foveation is going to be more noticeable. So let us now go over the methods. We test both approaches from our alternative hypotheses. We try the full stop method, where we omit movements altogether, and we do the dynamic foveation method, where we simplify movements based on the agent's distance from the fovea. What you see on screen here is the full stop method, with the green agents being fully animated and everything outside of the area having their animations completely stopped. The green area, is what we call the foveal area. The second method is a dynamic foveation, where again we have a foveal area with all the animations going in a green area. However, everything outside of it will have its animation rate calculated based on the equation on screen. The important thing to note from that equation is that it leads to a fall off like the one outlined on the right. Now, what you've seen here is our Unity prototype for this project. It should be noted that we simply do simple crowd simulations using the Unity's built-in nav mesh. And the scenes that I'm about to present to you in a second are derived from common crowd simulation scenarios. Very importantly is that our goal here is to evaluate perception, not to optimize implementation. Optimizing the implementation is going to be subject for further study. So let us now go over the scenes. The first that you've already seen is the Wonder Crowd, which is our unorganized movement scene and has agents going all over the place. The first of our organized movement scenes is Square Marathon, where they simply go around in a clockwise rotation. Similarly, parallel columns, except now we have two very distinct groups. Then we have intercepting crowds, where we have two groups repeatedly clashing into each other. And the intercept, where it's the same, except now the intersection is orthogonal. With these scenes, we go through two main studies. The first is what we call the flat screen test, which is our more structured test. And the second is a VR test, which is more unstructured. So, with the flat screen test, we try to go through our main hypotheses. First, to see whether the full stop or dynamic foveation method is better. Second, to see if more crowding leads to increased foveation tolerance. And third, to see whether structured movement leads to decreased foveation tolerance. The setup goes like this. We have a staircase test using all 5 scenes as per recorded videos. As they are videos, and because we're using a flat screen with no eye tracking capabilities, we have a red agent in each scene acting as the focus point for the participant. The participants were also observed while undergoing the test to ensure that the results are valid. Now, it should be noted that the foveation stages of the staircase test go like this. For full stop, we start from a very, very big foveal area, and we slowly shrink it as time goes on. For dynamic foveation, we have each stage increasing the foveation factor from the equation. What this leads to is a more aggressive fall-off. And these are the stages on screen. The staircase test, to be exact, proceeds like so. We start from no foveation, and every 10 seconds we go to the next stage. At any given point, the participant can press the spacebar button to indicate that they've seen foveation, and then ask to indicate where they've seen it. If the answer is valid, that is, there was foveation happening where they had clicked, then it counts as a valid response, and they go back 10 seconds to the previous stage. If they go again and detect foveation happening again at the exact same stage, it gets treated as a double confirmation, and the user goes on to the next scene. If, however, the input is invalid, say at the very first is invalid because there's no foveation happening in a place, then they get notified of this and they go back 10 seconds again to try again. The second It doesn't matter. The second study is the VR test, where we had users go through a modified Wondercrowd scene, wearing a head-mounted display with eye tracking capabilities. This is more unstructured. Here, we're simply playing with the foveation values to see if how low we can get before they notice it. So let's go over the results. First and foremost, here are the results for full stop. The red line here signifies where we believe the foveation starts to go into the user's fovea, so where we expect them to actually start noticing it. And you will notice that Wondercrowd to the very far right performs significantly better than the other scenes, and this has been proven to be a statistical difference. There is no statistical difference with the T-intersection scene, however, and we'll get to that in the discussion stage. There's very similar results for dynamic foveation. Wondercrowd performs a great deal better than every other scene, and the same applies for the T-intersect scene. Finally, once again, we can see here about where the user started to see foveation. Once again, the red line signifies where the fovea area begins. And we see that this is all quite close to the periphery, as we had hypothesized, quite close to the fovea area. And to give you a visual representation of how this looks, you will see here both methods about the means we discover this most effective foveation methods. And you will see that at any given point, did they stop again? Okay. At least half of the agents on screen are stopped at any given point. That is, the ones which don't have any highlights. For the VR study results, we've compiled the mean results of what everything means. However, explaining what these values mean might be a bit complicated, so I'm instead just going to show you what they look like in practice. Once again, the video is not working, whatever. You will see here that usually the user has the head-mounted display tracks the user's view, and you will see 3 highlighted agents here. These are the ones that the user has animated and the ones they're looking at, and everything else is stopped. It's a very similar result for dynamic, which actually works, and you will see that the highlight shifts. Once again, it's only a couple of agents actually being animated at any given point, and the rest are stopped. If you had trouble seeing how that looks like before, here's images of each to make it more clear. Now, in terms of performance, we've been looking at how many animation updates per second are happening, and we see that full stop performs generally better in the first 2 stages than dynamic at the very highest foveation stage. So generally, we believe that if full stop gets away scot-free, then we should be using that because it leads to better performance. So let's discuss the results. As we were saying before, Wondercrowd performs generally better than all other scenes. So we believe this confirms our hypothesis that more crowding leads to more foveation tolerance. However, as I mentioned before, we found that Wondercrowd has no statistical difference with the T-intersect scene. And we believe this is because in this specific scenario that you see on the right, we have 2 very specific groups which very high crowding, which generates a similar effect as it would in Wondercrowd. Thus, why they perform similarly. Nevertheless, because now we have confirmed that crowding leads to better tolerance, we believe crowding itself can be used as a driver for foveation. That's to say, if we have no crowding in one specific area, there should be no foveation there. But if we have a lot of agents in one specific part, there should be much more foveation in that specific part. We've also found lower foveation tolerance for scenes with organized movement, that is, the other scenes other than Wondercrowd. So does that confirm our other hypothesis that organized movement leads to lower tolerance? Fortunately not. You see, we've had a lot of false positives in the very early stage of the staircase test. A lot of the times in the very first stage where there was no foveation happening at all. So why is that? Well, we believe that what was happening is that the small movements of the agents were falling under critical flicker fusion, CFF. That's to say, our users were looking in one corner of the eye, and the models in the other corner were falling under CFF and looking like they're static, even though they're moving, which gets mistaken for our very own foveation. Moving onwards, regarding the 2 methods, full stop presented higher tolerance overall than dynamic foveation for all our scenes. It should be noted, however, that in our Wondercrowd scene, dynamic foveation performed generally a lot better, generally good as well, with some models going as low as 5 updates per second. So because of this, we believe the reason why full stop performed better is because of what we had hypothesized. The dynamic foveation causes flicker in the near periphery, and that gets picked up. But full stop doesn't suffer from this, because due to the lack of flicker, the lack of animations, they just keep going. Additionally, as we've seen, full stop has better performance overall. Therefore, we believe that between the two methods, full stop is the preferred option, despite what you might originally believe. Finally, we believe that screen space frequency can also be used as a driver for foveation. If you look at the scene here, for example, the warrior on the horse, they have a very shiny sword. If this person were to be foveated, even if the user is looking away from them, if the warrior were to swing the sword high while foveated, that will cause a lot of flicker, and therefore was very highly likely to be seen by the user. However, with very grouped up agents, as we were saying before, due to the crowding effect, we can still use foveation, and we can use it heavily. So in conclusion, we believe the full stop method is better than the dynamic foveation method because, 1, it is more tolerated by participants due to the absence of flicker. 2, in the best case scenario, it can lead up to 99.3% less animation update operations. And 3, because of this simple approach, it can be combined with other previous work to accelerate crowds, which is subject for further study. Additionally, we've confirmed crowding does indeed lead to increased foveation tolerance in the case of foveated animations, regardless of which method is used. And finally, the effectiveness of both methods have been confirmed during our VR test. That concludes my presentation. Thank you very much for listening.
So Vladimir, thank you so very much for a wonderful presentation. We have time for a couple of questions for Vladimir. Come on up.
Hey, I was wondering if there have been any ground truth tests for foveation in like the optics field that then you could tune your curve to see if maybe that could have been feel more natural for the dynamic method.
When you say optics fields, could you clarify a bit what you mean?
Like for people's actual eyes, do you have there been a study for the shape of the curve of foveation for them that you could then tune your curves to?
We had considered this. However, since we wanted to first verify whether foveation works as an idea, we've tried to keep this research relatively simple to see if the foveations work. That is something that we've been considering for this study as well. However, we've decided it's better subject for future study instead.
Gotcha. Thank you.
Wait, question over here. Thanks.
Hi, I have two. Something I might have missed earlier in the presentation was eye tracking involved in either the flat screen or the VR test for the moving foveation target, so that the fovea would be centered on where the eye was specifically looking.
Right. So the flat screen test didn't have any eye tracking due to the limitations of being a flat screen, and because we wanted to avoid any differences in the simulations, we had to use videos to ensure the same conditions for all participants. So there was no eye tracking there. However, the VR test, and if I go back a bit, I believe this is going to play. You will see here that the highlight does indeed move because that is eye tracked. The reason why we have the VR test is because we want to see whether eye tracking works in practice. And as far as we can tell, yes, it does. People only see about 3 to 4 agents being animated, and everything else is not noticed by them. Another question there?
I just had one more.
Yeah, go on.
What other principles of basic perception or even psychology would you want to explore in the future and apply to this foveation technique?
One other thing I've considered is, for example, for the organized movement scenes, is people starting to look in the direction of movement, so looking ahead of where the character they're tracking is going. So, for example, a bit of a predictive foveation was something we've also considered, and I believe that would be an interesting subject for future study. But so far, I think that would be it.
Thank you so much.
I was going to ask, like, you probably answered this, but what equipment did you use for, like, the eye tracking and the headset?
So that was, if we go here, the HTC 5 Pro Eye, which tracks eye movement at about 90 or 100 hertz, so it's very, very quick as far as I can tell. Any other questions? Oh, wait, one more.
Yeah. So you say you're saving computational power by using the foveated rendering. What exactly does the animation update contribute to that? In this study, I think you still have to look through all of the crowds to see if they are in the foveated area. So how does that compensate to the entire computational? Yeah.
You are right there. The implementation that we are doing here, as we were trying to test again perception, not to improve performance. Not to optimize the performance, is indeed quite naive, and therefore I am indeed looking through every single one of the agents here. However, we believe that because of how simple the full stop implementation is, it could easily be combined with some other acceleration techniques or other optimization methods to try and go through those specific agents relatively quickly. So yes, you're right. This is quite a naive implementation. However, we believe a better implementation which does take advantage of the lack of animations updates would indeed lead to a high frames per second improvement.
Okay, thank you.
And we have a little bit of time for one more question. Okay. Please join me in thanking Vladimir for a wonderful talk.
This laptop.
And our next speaker this morning is Matthias Molinar and Elmar Elsman. And they're going to be talking to us about transform-aware, sparse, voxel-directed acyclic graphs.
Welcome to the presentation on our paper titled Transform-Aware, Sparse Voxel-Directed Acyclic Graphs. Now, I realize this is quite a mouthful, so let's just go over it step by step. First of all, what is a voxel? A voxel is the cell of a regular three-dimensional grid. It's effectively the 3D equivalent of a pixel. Now, in our work, we're only really concerned with binary voxel grids. That is, a voxel can be in only one of two states. It's either empty or it's occupied. Now, this is a low resolution example, so let's have a look at a much higher resolution example, such as this. If we try to store this as a regular grid, it would require roughly 35 terabytes of memory. But with the compression method I'm going to show today, we get this down to 600 megabytes. So, how did we get here? Well, we start by constructing a sparse voxel octree. That is, we take our voxel grid and we split it into 8 equally sized octants, or in the two-dimensional case, 4 quadrants. And we're going to do so recursively. So every octant again gets split into smaller octants, which get split into smaller octants, until we reach our leaf nodes. Now, for illustrative purposes here, I'm using 2 by 2 leaf nodes, but in practice we use 4 by 4 by 4 leaf nodes in 3 dimensions. The way that we save memory from constructing this octree is by omitting all of the empty octants in our tree structure, such as you can see on the right. And this reduces memory usage to 11.5 gigabytes, which is an over 1000x improvement, but still not the 600 megabytes we were promising. So we're going to need to go further, and we're going to have a look at repeating patterns in our dataset. Because if we look at the leaf nodes of the octree that we just constructed, then you'll notice that even though we're storing 7 of them, there's only really 2 unique ones, which I've color-coded here with green and yellow. So what we can do is that we just store a single unique representative for each group, and then redirect the pointers of the parent level, like this. And we can do so not just at the leaf level, but also at the inner nodes, as you can see here. And with this, we reduce memory usage to around 1.5 gigabytes. So again, a 10x improvement. But we can go further. And that is by looking for more patterns. So let's have a look at this slightly different example here of the voxel grid on the left. And it's SVDAC representation on the right. So this SVDAC has 5 unique leaf nodes, but as you might notice, they look somewhat similar. First of all, 1 and 3, the two checkerboard patterns, are similar, and leaf nodes 0, 2, and 4 look quite similar. And this is what Villanova and colleagues also realized when they wrote their paper Symmetry-Aware SVDACs, which was presented at I3D in 2016. And what they argued is that they allow matching not only between leaf nodes that are equivalent, but also when they are equivalent after applying some transformation. And in their case, they considered mirror symmetries. That is, a mirror symmetry along the x, the y, or the z-axis, or a combination of those axes, which gives the effect of a diagonal mirror symmetry, such as shown here. Now, the SVDAC is not just going to store simple pointers, but the pointers will also have some transformation associated with them, which indicates whether there is a mirror symmetry along the x, y, z-axis, or a combination of those. Now, this process is applied not only to the leaf nodes, but also to all of the inner nodes. The authors combined this with a novel pointer encoding scheme to reduce the memory usage of their symmetry-aware SVDAC to around 930 megabytes for this specific scene. Now, this is going to be the starting point for our work. So the way that symmetry-aware SVDAC encodes their symmetries is that it's effectively a recursive reordering of the 8 child pointers at each node, at each inner node, or the 8 voxels at a 2x2x2 leaf node. Now, they only consider permutations which represent mirror symmetries, but we would like to look at all permutations. So there are many different ways that we can reorder the 8 children of our inner nodes, and we want to consider all of them like here. So how do we construct such a structure? Now we're going to start with either a sparse voxel octree or a sparse voxel DAC. In this case, I'll start with a sparse voxel DAC. And we're going to work our way up from bottom to top. So we start at the leaf nodes and we go up one level at a time. So starting at the leaf nodes, we want to remove all of the duplicate leaves. And we're going to do so by simply iterating through the leaves in any arbitrary order and checking whether the leaf that we're currently visiting matches anything we've seen before. So let's have a look at what happens at leaf node number 2. We take it and we consider all possible transformations. So we have a for loop over all of our transformations. For example, we might try the equivalent of a mirror symmetry. And then we check whether we've already seen the resulting pattern before. In this case, we haven't. So we move on to the next transformation. And that might, for example, be a rightverse rotation, such as this one. And in this case, we find that the new voxel pattern matches a leaf node that we've seen before, in this case, leaf number 0. Now, what we want to do in our SVDAC structure is store leaf number 0 and represent leaf number 2 from leaf number 0. So what we're actually interested in is the inverse transformation. So to go from 0 back to 2. And we apply this process to all of our leaf nodes. And then we want to move on to our inner nodes, but there's one more step we need to do. And that is that we need to compute the invariance of each leaf node, of each remaining leaf node, to all transformations that we are considering. Now, an invariance simply means that the leaf node remains unchanged after applying a certain transformation, such as you can see with the checkerboard pattern in the bottom row. And with that, we are now able to move on to our inner node. Again, we apply the same process of iterating through our inner nodes at this level at some arbitrary order. Now the first one is always unique because we don't have anything to compare against yet. So let's have a look at inner node number 1. Again, we try all possible transformations, such as a rotation to the right. And note that we are also updating the child pointers. So not only are we moving them around, we're doing so recursively, so the transformation associated with the children is also updated. Now we are posed with the challenge of how to compare two transformed nodes, so how to check whether the newly transformed node matches the previous nodes that we've seen before, in this case, inner node number 0. To do this, we first check whether the child pointer addresses match. This is equivalent to checking whether the children point to the same geometry, because if two children have the same geometry, they should have been merged into a single node or a single leaf by the previous step at the previous level, and thus have the same memory address. Second, we need to look at the transformations associated with them, because the two subtrees might be different after applying the transformations. And to do this, we rewrite the formula a little bit, so we can use our invariants that we computed before. So let's say we have one subtree, CK, with two different transformations applied to them, transformation J and transformation I. Now checking whether this is equivalent is the same as checking whether the subtree CK is invariant to the combined transformation, which is transformation J followed by the inverse of transformation I. And checking this invariant is very quick because we computed it in our previous step and stored it in, for example, a bit mask. Now again we find that we have a match and we store the inverse transformation. And we're going to do this for all of the inner nodes at this level. Then we're going to compute the invariance bit mask for all of the remaining inner nodes, and then we move up to the next level of inner nodes. And we're going to repeat this process all the way up to the root node. And with this, we see that we have quite a big impact on the number of nodes and leaves compared to the previous best method, which only considered mirror symmetries. Now there are some practical limitations though to this method, which is that we're considering many different permutations. So in 3 dimensions, there's over 40,000 ways we can reorder the 8 child pointers. And this is a problem in both in terms of compression time and resource usage during compression, but also the memory usage of the encoded transform-aware S3 because we need to encode 40,000 different options. So instead, we're going to suggest a much smaller and practical subset, which consists of mirror symmetries and a change of the coordinate system. So in 2D, that means flipping the x and the y axis, but in 3D, that means reordering the x, the y, and the z axis, and there are 6 different ways of doing so. Now the reason why this is so interesting is because it allows us to encode rotations. And when we apply this in practice, we found that we get very, very close to the results when considering all permutations, but now with only a small subset of 48 transformations rather than all 40,000. Now there's another problem with SVOs and specifically SVDECs in particular, and that is translational mismatch. So for example, we might have these two subtrees that store the same voxel pattern, so this little circle, but they're not quite aligned, so the subtrees aren't the same and we cannot match them. Now, if we look at the child subtrees, the child nodes, they're still different. So the child nodes here, these 4, do not match the ones on the left. There's no single match between any of them. And even the leaf nodes are completely different between the left and the right subtrees. So we can then not do any matching, and that's quite wasteful. Now, if we were able to do this, so we were able to match these mismatched subtrees, we will get an improvement of about 30% or 35% in some cases. So that's going to be our second contribution, finding these translational mismatches. Now, there's one part of the problem definition that I still need to talk about, and that is what I've termed destructive translation. So let's say I have this voxel grid, and I shift it to the left by 2. What happens to the voxels that fall off? Do I just not accept this transformation? Well, in this case, I tried that, but I found that this works better. So I do consider the transformation, and I just assume that everything that kind of gets shifted out of my subtree just disappears. And I've called this destructive translation. So then the question is, how do we do this matching? Well, first we take our subtrees and we're going to flatten them into just a regular grid. And then we're going to compute a descriptor. So this is very common in image processing and specifically 3D reconstruction. So a descriptor is just a magic number, a little bit like a hash function, and it tells us something about the voxel grid, in this case, in the top and the right directions. And in this case, we see that the descriptors here and here will match, which means that we can take this voxel grid and just shift it to the left and to the bottom, or to the bottom and to the left by 1, and we'll get the voxel grid on the right, left. Now the way that we compute these descriptors is using a hash function. So we run every voxel, so it's just a 0 and a 1, through a hash function. This gives us a magic number. And then we combine these hashes together with another hash function. The one trick that we do is that we only really start doing this accumulation of hash functions at the first non-empty voxel, so the first failed voxel. Everything before that just gets some sentinel value, like a special value such as 0. And we do this first horizontally and then vertically. So on the result of the horizontal pass, we now perform another vertical pass. And again, we start at the first non-empty voxel from the result. And this leaves us with voxel grids that have these descriptors at each voxel. Now we just need to do the matching. And for that, you can use, for example, a hash table, or you can put them all in a big array and then sort them. We do this for the leaf nodes, which in our case are 4 by 4 by 4, and at the 2 levels of inner nodes above them, so 8 by 8 by 8 and 16 by 16 by 16. There's 2 reasons for this. First of all, it's just very expensive to compute. The other problem is that the higher you go, the more potential translation amount you can have, and it makes our pointers bigger, and then we just run out of pointer space. Now, what we can also do by changing the order of the hash functions or changing their direction is find translations under symmetry and under axis permutation. So we could combine this with our first contribution. Now, with this, we are able to reduce the number of nodes and leaves by up to about 40 or even 50% in some cases. But this is not everything, because this is just the number of nodes and leaves, but we actually need to store it for it to be interesting. So we want to know the number of bytes. So for that, we also introduce a new pointer encoding scheme and a new node encoding scheme. So the pointers need to encode not just a memory address, but also a transformation. And we do that as follows. So we start with what we call transform ID. It consists of 3 bits, which store the symmetry, so X, Y, and Z symmetry, and the combination of those. Then we have another 3 bits for the translation X, so whether there is a translation or non-zero translation along the X, the Y, and the Z axis, so that's another 3 bits. And then we have the axis permutation, so how we reorder the X, the Y, and the Z axis. Now there's 6 different options there. So that gives us an integer, which you can optionally encode using Huffman coding. So we found that to save us a little bit of space. Now this is stored in the least significant bits of the pointer, which is then followed by the translation amount. So if there is a 1 bit for at least one of the translation axes, the corresponding amount of translations is then stored afterwards. And then finally, we store the actual pointer address. Now our inner nodes themselves start with a 16-bit header, 2-bit integers for each child, where 0 means that the child is just empty, so that's an empty octant. And 1, 2, or 3 indicates the length of the pointer, so either 16, 32, or 48 bits. Now, what we realized when doing this, because this is actually something that SSVDAC also did, the previous steps, so the variable length pointers, is that because our nodes are variable length, we're actually not using most of the memory addresses. So this is an example for it. Now, especially for the 16-bit addresses, we're able to address 65,000 unique numbers. But what we're actually doing is we're only indexing maybe 5,000 nodes. So it's actually quite wasteful. We're not really using all of those 16 bits very well. So our suggested solution is to create a pointer lookup table. So some of the most used pointers we store in an external lookup table, 64 bits each. And then our 16-bit pointers in our nodes are not really pointers, they're just indices into this lookup table. Because 16-bit is still not enough, and we found this lookup table to get bigger, what we did is that for the 32-bit pointers, we can also store a lookup table index. And we do this by prefixing the pointers by either 0, which means just a direct pointer, or 1, which is an index into a lookup table where the pointer is stored. And with this, we get to the results. So with our first contribution and all of this pointer encoding, we reduce memory by about 20% compared to the previous best method. And when considering the translations, we can go up to about 35 or even 40% compared to the previous best method. Now, this is an interactive 3D conference, so obviously we also have to look at rendering performance. And we see that our base method without any fancy pointer encoding is about the same speed as the previous method. However, when we add our pointer encoding schemes, we do add a bit of a penalty because there's an extra indirection, a memory indirection. The translations are actually, so our second contribution, are quite costly. And this is mostly because the traversal stack gets a little bit bigger. So we can run less threads at a time. Now, to wrap up, within time, we have a couple of limitations. So obviously the rendering performance is a problem. And the other one is the performance of the compression itself. So finding all of these translations can take a couple of hours on a desktop PC with multi-threading. The first contribution, so the permutation matching, that is quite fast. It takes about 1 or 2 minutes on a multi-threaded CPU. In terms of future work, I think it's interesting to look at even more transformations, because I think we only really scratch the surface here with these translations. And I think that SVDEX in general are just a little bit underutilized. So I would like to see them be included in, for example, neural VDB. And with that, I think I'm perfectly in time, and I would like to answer any questions you might have. And the code is also available online on our website.
You mentioned that the first file was several terabytes or even more. Is it possible, if I'm thinking about this right, is it possible to decompress only isolated branches of the octree as to not completely overwhelm any computer decompressing it?
The terabyte data is if you would just store zeros and ones in a continuous array, right? You can, if you just want to access individual voxels, is that your question?
Not individual voxels, but like individual sections of voxels, or even defined from one XYZ coordinate to another XYZ coordinate, or just as branches in the tree. Are you able to just decompress those subsections?
So in a sense, they're already compressed. So we assume that the entire SVDEC is stored in GPU memory. If you wanted to do something out of core, the octree approach is actually easier. It's easier to compartmentalize individual subtrees and then load them from disk. Because with these SVDECs, you would have like a whole bunch of interconnections. So SVDECs aren't very great for out of core rendering.
I see. Thank you.
Hey, great talk, and very nice to see that you can squeeze out 30% from something that already seemed pretty close to optimal. I have a question about something that I didn't fully catch about the destructive translations. So like you shown this diagram where like some voxels, when they are being translated, they kind of end up outside of the given like brick or
yeah.
I'm not sure about the terminology. So yeah, so I didn't catch like why you still consider this and this is not a problem in practice.
Well, we had to solve it some way, right? So if we would allow them to kind of shift off and then appear somewhere else, it might seem logical if you put it on the screen, but it might appear somewhere completely else in your SVDEC structure. So there wasn't really a practical solution, so we had to look at something else. And I tried just considering only translations if nothing falls off. I just found that the results of this were better. I get just more compression, more matches if I allow stuff to kind of disappear.
Thank you. I really liked your paper. I was wondering if your method also works with dynamic scenes that update in real time, or if it only applies to static scenes.
Well, that's an interesting question, because I actually had a paper on dynamic scenes at Pacific Graphics. So the second method, the translation, those are just too slow. I wouldn't worry about them. The first contribution, I actually think you can. So you need to iterate over all transformations. So effectively, you're multiplying by a constant factor, which is the number of transformations. In this case, 48. So it is possible. It's going to be a bit slower, but maybe with a couple of hardware generations, whatever, it should be totally possible to do this. The first contribution, so the permutations in real time.
And do you see any other optimization tactics you could use, for example, LODs, to further optimize your method?
Yeah, so I think in general, so we only display the highest resolution voxel grids, but I think in general, it's a little bit orthogonal to this specific, like the transformation-aware SVDEX. I think it's interesting to have a bit of a better look at LODs with SVDEX, because I don't think we're quite there yet. I think we do better.
Okay. Thank you.
Is it possible to employ the same techniques on the voxel dataset if the voxels can have more than just one state? So you mentioned 0 and 1, but could it be like RGBs or any other things?
So yes, you can. I actually tried it before. The problem is then you will only get reuse if not only the geometry matches, but the attributes also match. So typically the reuse just goes down very quickly. So there's actually kind of a branch of separate research on compressing attributes. And the way that we do this, I won't explain it here, but we effectively collect all of the attributes in a completely separate array, like a 1D array, and then compress them separately. And that's typically the best way to go around it.
Thank you so much.
Okay, please join me in thanking Okay, and our final presentation is from Yingrong Fang, Qitong Wang, and Wei Wang. And they're going to be talking to us about Aokana, a GPU-driven voxel rendering framework for open-world games. Okay, whenever you're ready. Thank you so much.
Hello everyone. My name is Arya Patel and I will be presenting this work Aokana on behalf of the authors. Unfortunately, the authors weren't here for some reasons and I will be presenting on their behalf. So let's begin. So Aokana is a GPU-driven voxel rendering framework for open world games. In recent years, open world games have become increasingly popular among players. GTA is one of the most famous open world games in the world. Genshin Impact has sparked a wave of interest in open world games on mobile platforms. The recently game Neverness to Everness is also highly anticipated by players. Open world games typically feature large game maps which require a vast amount of content and artistic resources to populate the game world. However, the large-scale maps typically require for open source games necessitate substantial cost and extensive human resources for asset production. This unaffordable cost deters many low-budget teams and independent game developers from developing open-world games. But game developers can always come up with workable solutions. How about voxels? The voxel representation of 3D geometry is highly intuitive and structured. Voxel assets of open world maps can be efficiently generated in bulk through randomization or procedural methods. Independent developers can use procedural generation algorithms to quickly create vast voxel maps. As a result, more independent game developers are turning their attention to stylized voxel games such as Minecraft and Teardown. Taking Minecraft as an example, where each block is sized at 1 cubic meter, an almost infinite natural environment map can be efficiently generated by adding random noise. However, voxel-based approaches also possess some technical challenges. For example, when developers aim to create a large artificial city map, they need to pre-store the complete map data on disk and selectively load the necessary data into both memory and VRAM. Simply using a mesh to represent voxel scenes is not always feasible because meshes can occupy a very large amount of VRAM. Loading the entire map data into memory at once can create significant memory issues, especially resulting in out-of-memory errors. If the game requires fine-grained voxel details, the storage cost will further escalate. For open-world games, view distance greatly affects the player's experience. Players want to see distant scenery. However, as there are many more distant objects than close-by objects, loading the object distant scenes is the main consumer of the RAM and VRAM. How to process distant objects with low memory consumption is a main challenge for real-time rendering performance of open-world games. Since distant object appears smaller, we don't need to maintain all the details. Therefore, we need to tailor a customized level of detail system for voxel games. To wrap up, our goal in Aokana is to design a rendering framework for open world voxel games that can offer an extremely long view distance for large world maps, but with a high performance rendering and low VRAM usage. We now present our solution, Aokana. Aokana primarily is composed by three components: sparse voxel DAG LOD chunk preprocessing for low memory consumption, and world partition and streaming, and a GPU-driven voxel rendering pipeline for fast rendering. We first extend sparse voxel DAG, SVDAG, by using multiple SVDAGs with different level of details to represent the entire scene. Sparse voxel DAG is a technique that represents a voxel chunk in the world. It is a data structure obtained by merging isomorphic subtrees of a sparse voxel octree, which can greatly compress the geometric information of voxels while still retaining the ability to perform ray marching. Due to pointer-linked structure of SVDAG, it is not cache-friendly. As the voxel resolution continues to increase, the depth of the SVDAG also increases, leading to more indirect jumps along the path from the root node to the leaf nodes, which results in memory access bottlenecks. To reduce the number of indirect jumps, we propose that instead of using a single SVDAG with a large depth, multiple SVDAGs with smaller depths should be used to represent the entire scene. To use the multi-SVDAG design, we first divide the entire open world game map into a series of axis-aligned cubic regions, each region maintaining a chunk of resolution 256 cube voxel. For each chunk, we employ sparse voxel DAG for compression and representation. As a result, the entire open world voxel map is segmented into several sparse voxel DAGs. Each chunk contains two types of information: geometric information indicating whether a voxel exists as a position XYZ, and color information specifying the color of the voxel at that position. We decouple the geometric and color information of the chunk and compress them separately. For the compression of geometric data, we employ a method similar to SVDAG, which involves merging isomorphic subtrees of the sparse voxel octree to form the DAG. A node in the DAG is represented using 8 to 40 bytes. The first 4 bytes of each node's data contain a 32-bit head node, where the lowest 8-bit represent a child mask that indicates the presence of corresponding child nodes. The following 4 bytes store the number of leaf node in the subtree rooted at that node. The final 0 to 32 bytes contain pointer to the child nodes with the number of pointers corresponding to the number of binary ones in the child mask. For the 3 deepest layer of the nodes, we consider them as individual 4x4x4 leaf chunks and utilize a 64-bit bitmap to represent the geometric information of the leaf chunks. We further decouple color information from the geometry data for higher compression ratios. Each node in the SVDAG records the number of leaf nodes in the subtree rooted at that node. By accumulating the count of child nodes along the path from the root node to the leaf node, we can determine the index of the current leaf node in the depth first search order. This index is then used to store the color of the leaf node in a separate independent color array, which is subsequently compressed. We simply use run length encoding to compress the color array due to its high compression rates on ray marching performance. To reduce VRAM usage, we implement a LOD mechanism for the chunks. We consider the smallest voxel chunk, which maintains a resolution of 256 for a region of size 256 cube, as LOD0. Using a method like octree, we aggregate 8 LOD0 chunks into a single LOD1 chunk, which retains the same resolution of 256 cube. Thus, each voxel in an LOD n chunk is derived from the aggregate of each 8 voxels from the LOD n-1 chunks. This process continues recursively until the entire world is aggregated into a chunk. We maintain an implicit octree on the CPU side to organize the chunks and filter those that needs to be loaded. Whenever a chunk is influenced by camera changes, we initiate a coroutine to perform a recursive search starting from the root node of the octree. Each time a node in the octree is accessed, we first check whether the region it manages contains the LOD chunks. If it does not, we continue the recursion downwards. If the current node does not contain LOD chunks, we use an error formula to determine whether the current LOD can satisfy the visualization quality requirements. If the LOD error is greater than 0, further subdivision is necessary. If the LOD error is less than 0, the chunks is marked as needing to be loaded. The LOD error formula is based on the position and size of the chunk as well as the position of the camera. Stream factor is a predefined hyperparameter. A higher stream factor indicates that distant objects will have more visual depth, which correspondingly require more VRAM. When determining the loading order of chunks, we can prioritize loading the chunks with higher LOD levels, allowing us to directly remove all child blocks associated with that chunk to free up VRAM. When there is sufficient space in the VRAM, chunks that are closer to the player are prioritized for loading. We also design a GPU-driven rendering pipeline for efficient SVDAG-based voxel rendering. The entire rendering pipeline mainly includes several passes: chunk selection pass, tile selection pass, built high-Z pass, and ray marching pass. All the passes are executed in compute shaders. Our custom passes are inserted after the opaque pass and before the transparent pass in the forward rendering pipeline. It can certainly be extended in a deferred rendering pipeline as well. Before all our passes begin, all opaque objects in the scene have already been rendered. We compute the axis-aligned bounding boxes for the portion of each chunk that contains valid voxels, and in the chunk selection pass, we use custom culling based on the bounding boxes of the chunks to eliminate those that are currently not visible to the camera. Due to high cost of ray intersection with chunks representation by SVDAG, we aim to minimize ray and chunk intersection to reduce overdraw and ensure rendering efficiency. In the tile selection pass, we divide the screen into a series of tiles with 8x8 pixels. For each 4x4 tiles, we allocate a thread group, assigning one thread to each tile. We project screen rays from each tile to determine which chunks that passed the chunk selection pass contribute to the current tile. For the chunk currently occupied by the camera, we perform ray SVDAG intersection test, while for other chunks, we conduct ray box intersection test. We use this intersection depth value as the depth value for the current tile. As we perform high-Z culling on these tiles, after the tile selection pass, we identify which chunks contribute to the corresponding tiles, ultimately resulting in a series of tile chunk pairs. We use a custom tile info structure buffer to store the coordinates of each tile that passed the intersection test and the corresponding chunk ID. In the build high-Z pass, we construct the high-Z texture from the depth information of the current frame's depth texture. Since the camera may be moving at high speeds, using the previous frame's high-Z texture for tile culling may not be accurate and could lead to incorrect culling. Therefore, we re-execute the tile selection pass, performing an indirect dispatch compute shader on all tiles that were culled in the first tile selection pass. We use the current frame's high-Z texture to reapply high-Z occlusion culling, filtering out all the tiles that were incorrectly culled. For all tile chunk pairs filtered in the tile selection pass, we perform an indirect dispatch compute shader to initiate the DAG ray marching pass, assigning a thread group to each tile. We use a 64-bit visibility buffer to record visibility information. In this pass, we employ a ray intersection method similar to that in ESVO to calculate the intersection points between each pixel on every tile and the corresponding chunks SVDAGs. We use interlocked max to write the depth values, normal information, chunk IDs, and a voxel coordinate at the intersection points into a 64-bit visibility buffer that matches the size of the screen. In the color resolve pass, we divide the screen into 8x8 tiles and allocate a thread group to each tile in the compute shader, assigning one thread to each pixel to compute its color. First, we retrieve the information for the pixel from the visibility buffer. If the information is valid, we extract the normal, chunk ID, and voxel position. We then calculate the DFS order of the intersection node of the SVDAG based on voxel position. Using the DFS order, we perform a binary search in the color block array to find the corresponding color block. Finally, we shade based on the normal and the color, writing shading results into the color texture. If using a deferred rendering pipeline, you need to first write these informations to the G buffer before proceeding with the subsequent deferred shading process. We implemented Eokana using the RenderGraph API in the Unity 6 game engine with Vulkan as the rendering backend to evaluate its effectiveness. We conducted experiments on 3 open world voxel maps, San Miguel, Sponza, and Greenfield scenes. Greenfield is derived from a popular Minecraft save file. It can represent a real game scene with a large-scale modern city, allowing us to evaluate our method's performance in real open-world games. We first compared the storage sizes in scenes with different resolution. Our method has a lower VRAM usage compared to other methods. We only need to retain about 2% of the original data in VRAM, while the VARM usage is reduced by up to 9 times compared to hashtag. This image gives a visual comparison of the level of details between our method and the existing gaming software. Our method can better preserve the visual details of the distant objects compared to Aeonid and Minecraft plus Distant Horizon MOD. We then compare the rendering time of our method and other methods for a single frame. The rendering speed of our method is faster than that of hashtag, achieving a maximum speed of up to 4.8 times in the test scene, and our method's rendering speed is less sensitive to scene resolution. We now compare the time to compute primary ray intersection points. Our method has advantages in high resolution scenes and real open world scenes, achieving a maximum speed of up to twice that of hashtag in the test scenes. This is a demo of Eokana's open world exploration. Eokana enables players to roam seamlessly through the open world maps while maintaining high quality for distant scenery. To conclude, in this paper, we proposed Eokana for real-time rendering of large-scale voxels in open-world voxel games. It incorporates a level of design mechanism and a streaming system enabling seamless map loadings as players traverse the open-world game environments. We designed a correspondingly high performance GPU-driven voxel rendering pipeline to support real-time rendering of the voxel scenes that contain tens of billions of voxels. Aokana can be directly applied to existing game engines and easily be integrated with mesh-based rendering methods. In future work, we plan to support voxel rendering with various material models. We also plan to better integrate Aokana with the traditional mesh-based methods to seamlessly support mesh-based collision detection, navigation systems, and other modules. Thank you everyone for your attention.
So thank you so very much for a great presentation. And I believe we have Ying Rong is online and available to answer questions on behalf of the Aokana team. So we have a question here. So I think if you would just come up, if you wouldn't mind coming up to the, just here for the webcam. There we go, perfect, thanks.
Hello. Hi, can you hear me? Are you able to hear me? Yes.
Oh, wait. It's my fault.
Oh, okay.
Just 1 second. So stay there. 1 minute. Okay. Okay, let's try again. Say something.
Hello.
Okay, let's try.
Hi, can you hear me?
Do you hear us? No?
Yes.
Oh, good. Okay. Sorry. It's just latency. I had a question about in the voxel-based environments. I don't know how small the voxels are supposed to be, but if they're like to a substantially small sizes to almost replace meshes, is there any specific methods for handling either just basic object collisions or BRDF shading for surfaces other than 90 degrees, like collections of voxels that represent different angles, or was that not part of the purpose of this? Yes, if you have a set of small voxels that go at say like a 30-degree angle rather than other than 90, are there ways of handling collision with that surface, or would it act still just like a set of smaller blocks?
There are many ways to achieve it. The first way is you can think also come in the CPU side and you can in CPU way detect. And another way is to in the some in the CPU memory and do it in computer and the result by initially back.
Oh, I see. I had one more question. It was interesting that you in the presentation distant horizons was mentioned, simply because of the operation of it more rendering more baseline 2D image map in the background. Was a method similar to that considered as part of the set of these methods, or was that or was it just included as a piece of comparison? Earlier in the presentation, the distant horizons mod was used as a comparison method for a level of detail for faraway objects. Was a similar method to how that mod operates through, I believe it's a 2D image representation of the faraway objects. Was that considered as a method used in this voxel based methods, or was it just meant as a point of comparison? Sorry, it wasn't actually that irrelevant of a question. Sorry about that. Thank you very much. It was very impressive.
Thanks very much. And you could possibly just follow up via email with them. And I think we have time for one short question. Question for Ian Wrong.
Hi, I have a question. So you do compare to hashtag, and I was wondering, because it went over quite quickly, why you chose for a simple RLE compression of the attributes rather than using something like the Delaunay's method, like a better color compression method for the colors. Like, what is the trade-off between compression ratio and performance?
Say again?
Sorry. So you use a simple run length encoding of the colors. Could you elaborate on the performance and memory compression of that system versus hashtag?
I use a simple strategy to compare because in your video game, the photo is not only the color, but I had some gameplay method. So for gameplay reason, it's difficult to just use more advanced techniques. Because we want to use both the value, not only color, but some gameplay meaning.
Okay, thank you.
Time for one more question. Breathing around. Okay, over here. Yeah, if you just go. It's just about there. Thanks very much.
Hello. Ready to go? Oh, yeah, some hiss. There we go.
Okay.
All right.
Can you still hear us?
Can you hear me? Can you hear me? Yes.
Okay, just change the audio. Okay.
Okay.
And now?
Can you still hear? Yes, you are still able to hear? Okay.
Yes.
Yeah, just had a question because I noticed you used Unity 6 and the Vulkan backend. I was just curious if you explored doing any of this on mobile devices as well, especially because like Genshin Impact was mentioned at the beginning.
Sorry, can you repeat it again?
Oh, yeah.
Sorry, can you repeat?
Yes. So I saw you used Unity 6 with the Vulkan backend. So I was curious if you tried running any of this on mobile devices.
I haven't tried it.
No? Okay. Do you have any... Sorry, go ahead. Do you have any...
It's only wrong. See?
I'm sorry, I missed that. do you have any thoughts on how you might adapt this to run optimally on a mobile device versus what you have here, or where you would expect to see issues?
I haven't tried it on mobile platform yet.
Okay.
I'm not sure the 16-4-bit visibility buffer is work on my platform. I haven't tested it.
Okay. Yeah. Thank you.
Okay, thanks very much. And with that, I'd like to have you join me in thanking Yingrong and the AOCANA team for a wonderful presentation. And that concludes our session on animation and voxels. So please join me in thanking all the teams for presenting such amazing work, and in particular for their great presentation skills as well. And just to remind you that the voting for best paper is still open. So thank you very much to everybody.